Okay. So if you see, this is the input features, and these are the weight, the random weight. Then the equation would be like this to get the output. And to get the output, actually, we have to apply one method, that is the activation function. So let's see this example. So here, if you see, these are the three features with 4 records, and the output is a binary problem. Let's take at the first step, train the neural networks, and based on that, we wanted to initialize the random weights. So weights will be coming here. So weights will be coming at this point. This, if you see this one, 1.4, 2.7, and 1.9. So this will be occupied in these nodes in the memory units, and then a weight will be inputted here and here as well as. And if you see the every connections that is from the nodes to the hidden layers. So if you take the input here, the expected output is 0. But let's say we get the equations where we get the 0.8 output. So then what we'll do? How the deep learning used to learn from this network. So the 0 minus 0.8, that is 0.08, is going to be the errors. And on the basis of that error, we are going to do some adjustment on the networks. So if you see here, the adjustment will happen because it is connected for this output from all these things. So there will be some adjustment happen in every way, not only single way, but everywhere. Here, there, here. Again, there is just 1, 2, 3, 4, 5, 6 connections are there, right? From input to output. So whatever flow is there from these 1, 2, 3, 4, 5, 6, and 7, 8, 9, everywhere adjustment will happen. So here again, let's say feed it through to get output for the second or this one layers, 6.4, yes. So let's say this is the 1 is expected, but we getting the 0.9, 1 minus 0.9, 0.01. So this is the error. So to get into the adjustment of this error, so we do apply what we do actually. So I'll show you that the diagram where it says that this is change in the delta, change in, we cannot do any other formula, but the most important enhancement has been done in deep learning is like to get it, we do change in error with respect to weight. So what is the adjustment need to be done here? Let's say here it is some weight is there, W is equal to 0.3. So then it will be like a change in that weight with respect to the error. dW by delta of W by dW by dE, right? Errors. So that's how the changes will be seen, and there will be adjustment will happen on these nodes. But then how neural networks process? From here it comes here, also here, and again it goes to the output. But then based on the error, so it will find out the change in error with respect to the weight, and then the adjustment will happen on this weight, everywhere, and then reverse networks will process. So from this output is try to get this input. So again, it will process from here. So it's a bidirectional move will happen. So repeat this thousands or millions of times, each time taking a random training instance and making slight weight adjustment. Now I tell you that, so there are 4 records are there. So these 4 will fill up this right. So because every row is considered once, right? So the number of features will be here. So it will fill up in these nodes and it will process and for every records we are expecting some output. So then the errors can be find out. So absolute error, that is ABS of 1 minus 0.9. So based on that, what happens? So if you have seen the neural networks run, so in every epoch or iterations, it runs whole training set records. If there is 100 records, all has to be one rows, then second rows, then third rows. It has to process through these networks and find out every time error. So what you see is mean absolute error. So the mean of the error and the accuracy. That is a mean you see. So every step there will be some error and adjustment. So what you see in the output is the mean ones. If I go back and show you the PPT, so I show you the network, so you'll be realize that. So if you see this one, 8,000 samples records were there. So every time it runs and gives the accuracy and loss. The loss is the mean of the loss, and the accuracy is again the mean. So it's the for all the 8,000 records, what is the accuracy? This is the mean of that, right? So and you understand that my mean is can like it by total number of samples divided into 100, and this is the mean of the loss. Again, it will fill up in the all networks input and go through the hidden layers and get the output accuracy. So every time it is working on that. So in a decision boundaries perspective, how it works. So if you see, if it is a decision boundary has to work like this, and present training instant adjust the weight. Let's say adjust the weight means what? Every time adjust the weight, ultimately you are creating a graph, right? Machine learning is you have realized that it's a pattern in X, Y, Z, and how many different features are there will create number of dimensions, and accordingly it says find out dy with respect to x-axis, dy with respect to z-axis, and so. And then it find out either a straight line or a logistical curve like that. So if it is like this, so based on the initial random weights is there, and let's say you got like this. So second times it may happen like this. So it's not necessary that every time a weight adjustment has been done, right? So weight adjustment has been done, let's say for how many records? So the records, maybe 100 records are there. So everywhere there is a weight adjustment will happen. And sometimes this has to go like this. It may go a little bit up and it's a misclassification, correct? So it may go up. But over a time, because it's a kind of a trial and error of this weight adjustment, over thousands and millions of times when it works, so ultimately it learns to smooth and find a good decision boundary. So over a time, it may not happen. So it may happen that it should go here and it is going up. So next time may it go up, it's down, down. So at this point, after let's say 100 iterations, maybe it's able to find out where it should go. And like that, it's find out every time based on the weight adjustment. So when I say weight adjustment, think of that at this point weight is something, this point something, this point something like that. And let's say over a time it learns, and it takes a lot of time to get into such a graph. So the point is that weight learning algorithms are dumb. They work by making thousands and thousands of tiny adjustments, and each making the network to do better at the most recent pattern. So it may not be doing good at a single instance, but in thousands of times or millions of times, it is expected to do better. One minute. So if fx is a nonlinear, a network with one hidden layer, in theory, it can learn perfectly any classification problem. So what is I said like initially, if there is only one hidden layer, so then it is what? It's a simple neural network. A set of weights exists can produce the target. So it is just like one hidden layer is something like this, right? So it's a simple network. If fx is linear, then neural network can draw straight line decision boundaries even if there are many layers of units. But fx is linear, but the neural networks solve the problem of non-linear problem mostly. It's not linear. So they can draw complex boundaries and keep the data unchanged. So when it is a data is we are expected to solve regression problem. Let's say the Boston dataset problem. If you wanted to solve using linear regression, then so we'll see that in example. So we do least square approach. So error is there, right? So least square approach is mean squared error. Sorry, the mean squared error is the for use for regression problem. So, but when we use uh, when we have non-linear, so it may we go with tangent or ReLU activation function or sigmoid. So what is the difference? Now, if you see SVM and all, what they do, they increase the dimension so that you can put a straight line between them. So how they solve and looks like circle or something shapes. How it actually do? It increases the dimension, and what neural networks can do, it can take in the shape of, it can do the adjustment and learns over it. Let's see this example. So we are not here today to start with the CNN problem, but for this to understand how neural networks learn. So we'll be seeing the example of how it detects features. So let's say this is a handwriting digits. So that the difference is like the people in hand making handwritings can be like in any shape. So it is not of the base. So let's say to solve this, we take input layer, hidden layer, and output layer like this. So many features, maybe the more hidden layers will be there. Definitely has to be. So as I told you, like you can take divided by the uh, divided by 2 if you do so ultimately how many you can do. So the number of equally distributed, if you have a 24 features, what you will do, you can do that the output plus 6 is 18 or 7 is 21. So it should be sum of that all low. the hidden layers plus output should be equal to the input layers. So hidden layer units become self-organized feature detectors. So I will tell you what it is happening here. What does this unit detect? So it has to do something like, if you see here, so here is a strong tendency that it is a strong signal for a horizontal line in the top row. So it is taking, what it is taking actually, this is 9, right? So this is 9, and we are playing with the horizontal and vertical lines. So if you put this like this, so as there is not a single, I mean there is only a single black spot is there, so it is expecting like this is a horizontal line, and it's a horizontal line. Now if you take it is like this, so what is that? Signal of a dark area at the top left corner. So or if you take this one, dark area is there, so you understand, I mean just like that. So if you take this much of pixels, so a dark area is there. If you take this much, it's a horizontal line, and there is like a features. I mean, what I want to say, if it has to be adjusted with a 9, it will say that 9 has a black spot in here or what, and this is a black spot or not. So what features might you expect a good neural network to learn? So let's say here vertical lines. So if this is one is what looks like a vertical line, correct? So 4 is might be again it takes as a vertical line, and this 9 is again a vertical line. So now at this point it might think as a horizontal line because it looks like horizontal. Here it might looks like a horizontal, and it looks like a horizontal. What this looks like? A circle. This also circle and this also circle. So in the hidden layer, it is not enough to, one hidden layer is not enough to know that is 6 or 2 or it's a 6 or 0, because it has also a circle, it is also a circle. Maybe at a point when it takes a horizontal line on the top corner, so it will find a black dot, and here it will not find anything. So then it will consider, okay, it might not be 0, because 0 should have a, right, 0 should not have a black spot here. Then might be it will, in the next layer, it will try to find it between 6 and 9. So it is 6 or it is 9. So then what it will say? So again, it will find at this point, if you take a, it may looks like a horizontal line, and here it will say some vertical line. So then no, it's not 9. Then it might play with what? There is no options there, right? So it can play with 2, and 2 is the option. So 2 already we have said, 2, 0, and 9. If it didn't find, then ultimately it will go for the 6. The chances that it will find out, it's more on the 6 side. So this how it requires neural networks to process the information many times to actually understand what is the desired output and what is the actual output and what is the minimum error between that. Now let's say if you put this much of data in as an image, so what we'll say that always we say that the image is of pixels, let's say 32 into 32. What does it means? 32 bit into 32 bit. So 32 bit, when I say, So 32 pixels in the horizontals, sorry, this way, horizontals, when we say that 32 pixels is there, so that means 1, 2, 3, 4, 5, 6, and so on. Here how many is there? 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. So 10 columns you have to find out. Then what should be the input layers of the networks? 10. Alright, it's number of features. And similarly, this is 1, 2, 3, 4, 5, 6. So 6 is the record. So we don't bother about that. The neural network should have the number of features. So we should have an input layer of 10. So because every time it will have a conversion, this 10 inputs, then this 10 inputs, and this 10 inputs, right? So it will be like that. So when it go always 10, so it's what is the maximum? So there may be more than that, but the output is also how much? 10 only, right? So out of 10, what is the probability that it is 0 or 1 or 2 or 3? That is, we try you have to find out using those earlier steps. So it will do this kind of principles and do this adjustment to understand 0, 1 or 2 or 9. But I might think that it's clear that what should be the input layers and what is the expected. So the addition of all hidden layers plus output should be is equal to input layer. So it is looks like this. Again, if you see detect line specific position, so if you put a like this, so it is detects a black spot in that. So this kind of horizontal lines can find out. So what is that in the pattern? So whenever you ask this 9 to find out if it is a 6 or 9, so it will check at this point pixels that what it is of what type, and this 9 and 6, what is that? 6 in this presence is uh, color is what, right? So based on the color, it will find out. Based on the RGB, it can detect what should be this, right? So this is trying to match the features. And the features here is what? Every dotted pixels. So what it talks about? Sorry. So what it talks about? Horizontal line detectors. So these are horizontal line detectors. This is vertical line detectors. And this is circle. So this kind of different circles can also detect, correct? So the feature detectors can be many different ways. So these are the complexity on the basis of which we are using TensorFlow or something. So we cannot write our everything. So now we have realized probably that neural networks using TensorFlow has designed our nodes. We just have to place in the methods what is the input layers. So it creates the nodes for us. We don't need to create. So if you can write your own program, create nodes and process, you can write your own neural networks. There can be memory leakage and all. There can be slowdown in your program. But then TensorFlow is already handling it in not only single networks, but in a distributed environment also. So there is a multiple layers make sense because if you see this one line, one instance might be we are handling with this, second instance this, third instance this. So when you have a many layers, so the we can do many type of adjustment, and there is a more possibility of we can get the better output. But as I say, so it is difficult to keep previous information. So if you get hundreds of deep neural networks, so might be when we reach here, we don't have the information what is saved here. Then what is the make sense of it? Then your neural network will again low perform. So that's why as per the number of features input, this middle layers, addition of the middle layers plus the output should be is equal to input. So the brain also works in in a many different instinct. It takes the many different decisions and ultimately gets into one. So it is capable of learning two underlying features and the feature logic, and therefore generalize very well. Generalize means that we're getting the right output. So the weight learning algorithms, so before deep learning was not good, and using deep learning or multiple layer, so it can do that adjustment. So as there is a multiple things exist, you can save this kind of information backwards, nodes, whatever save, and we don't play with that for neural networks, but recurrent neural networks, there we require the old information. So here the weight adjustment is required. That is why we have multiple layers. We do the train the first layer, then we train the second layer, this layer, and this layer. And finally we get to that. So it is the repetitive, it is a one epoch, right? For all the nodes, is a one epoch. So each of the layer is trained to be an auto-encoder. Basically, it is forced to learn good features that describes what comes from the previous features. So good features means what? So if it is a black spot is there, might be it is 6 or 9. So that information, the important information is talking about good features. So the autoencoders is trained with an, what is autoencoder there? So it's trained with an absolute standard weight adjustment algorithm to reproduce the input. By making it happen with many fewer units than the input, this forces the hidden layers to become good feature detectors. So you can see this like a compression. So there is a, let's say 13 input, so we make it as a 6 hidden layers. So what is that? We are taking all the important features from here and we are playing it, we are placing it here. Okay. Yeah. So this session has been, I think, 10 minutes going to. I am just reconnecting it. So please connect it back.